Okay, so we're starting chapter 16, and we're talking about waves. So waves are important, and one of the most important reasons is that they're responsible for everything that you see and hear. And so we have an example here of our loudspeaker. So we have inside a loudspeaker, there's a membrane, and the membrane moves back and forth, and it pushes molecules. And so you can see here there's a tight grouping of molecules here, and then a void, so no molecules or very few, tight, void, tight, void. And so you can think of this maybe as like a sine wave. So think if I were to draw, let's see, if I were to draw a around this, right? So here is my source, and I have, say I draw the sine wave that's like a peak here, and then a trough here, a peak, a trough, a peak. So I could represent this as a sine wave like I do for waves. We also can think about light waves. So this is a common representation of waves where we can think about radio waves here. These are electromagnetic waves. So we'll be talking about electromagnetic waves and sound waves. But radio waves are electromagnetic waves. You might think they're sound waves, but as we learn more about it, you'll find that radio waves are really electromagnetic waves. But these waves change in frequency and wavelength. You can see increasing frequency on the top and decreasing frequency on the bottom, so they're inversely related. And we can see that light, what we can see is just a tiny part of the electromagnetic spectrum, where red right here is a lower frequency and blue is a higher frequency, or you can think of it like red or blue is a lower wavelength and red is a higher wavelength. So just note that the speed of sound in air is around 340 meters per second, whereas the speed of light is 3 times 10 to the 8th meters per second. So a giant difference, which is why we see lightning before we hear it. And then the range of human hearing is 20 to 20,000 hertz. So that's our range. So there's lots of frequencies that we don't hear. There's 2 types of waves. There's transverse waves. And for transverse waves, we can think about a rope, right? So in this example, imagine that you're holding a rope and you wiggle it up and down or jiggle it up and down, and you create this wave that moves along the rope. So when I first start, the wiggle would be here, right? And then the wiggle would be here, and it moves along. The rope doesn't move, right? It doesn't move to the right, just the wave moves. So the rope is the medium, and the rope moves up and down, and that gives us the transverse meaning of the wave. So our wave moves to the right, right? This motion moves to the right, but the actual medium stays right there. And one other example, in addition to like a rope, wave on a rope, is light. Light is a transverse wave. We can also think about longitudinal waves, and I gave you that example about loudspeaker. And this is another example, right? So sound is an example of longitudinal waves, but we can also think about like a spring or a slinky. And if you held on to a slinky, right, you could move it back and forth like this, right? And you would have some of the coils would compress, a bunch of them together, and then you have some that were further apart, like here, and then some together, and then some apart. And so that's you can imagine that the wave is moving to the right, and that compression, and then that like empty space where there aren't as many, right? Where they bunch up is the peak of the wave, and where they're not as many as the trough of the wave. And so just think about like for transverse waves, right? The motion again is distinct from the motion of the medium. The medium is moving up and down. That rope is moving up and down, but the whole rope doesn't move to the right, whereas the wave is moving to the right, and it has a speed that we designate as v. So v for velocity. Some wave characteristics, right? So the amplitude of a wave is just the measure from the axis to the peak, right? Or the axis to the trough, right? And so that's an amplitude, and usually we'll just give it a value. Say in this example, maybe it's 1 meter, or maybe it's 0.1 meter, something like that. And the peak here, where it's above the axis, is called the crest, right? Where it's below the axis, it's called the trough. So we can also measure what the wavelength is. So the distance from one peak to the next is called the wavelength. And so we have some terms that you need to know. So lambda is representing the wavelength. Capital A is representing the amplitude. Frequency is the number of waves that go by in a certain given amount of time. And so you could imagine that if my wavelength is really big, I'm going to have less wavelengths go by. And if my wavelength is small, I'm going to have more wavelengths go by. And so that's represented by something we call the frequency. And the period, the time from one peak to the next, right, we call the period, and that is equal to 1 over the frequency. And then finally, when we're using trigonometric functions, we use omega, which is the angular frequency, and that can be represented by 2 pi times the frequency, or 2 pi over the period. So the speed of a wave, for all waves, we can talk about the speed as the frequency times the wavelength. So V is equal to the frequency times the wavelength, and we can manipulate this equation to find the frequency or to find the wavelength if we're given the other values. For a wave on a string or a chord, like a string instrument, like a violin or a guitar or something like that, then the speed of the wave, V, is given by the tension in the string divided by mu, and mu is the mass density. And so the mass density, mu, is just mass over length. So that's what you need to know about the wave on a string or a chord. We can represent waves graphically. So we have snapshot graphs and displacement graphs. And a snapshot graph just shows the displacement of the whole string or the medium at one instant in time. So imagine, you're standing there and you're watching somebody wiggle a rope, right? And if you just had your camera out in that instant, if you just took a quick snapshot, that would be what a snapshot graph is. So it's the name illustrates what it is, right? So as this person wiggles their rope, their string, at some instant in time, we took a snapshot, a picture. And so that's one instant in time. And say in our example here, it's t equals 0.94 seconds. Right at that time, we took a snapshot. And so we can see what the wave, what the string looked like at that time for all positions, right? So we can see that there was a peak a little bit before 1 meter, right? And we can see that, it's a little less here at 1.5 meters. We can see it's 0 over here at on the left, right? And so this is just like looking here, the particle located at 1 meter. So that's the snapshot. And so if we want to just look at what some things about it, we see that this is the curve shape at that time. And we can see that this is the leading edge, right? So the leading edge is less steep than the back edge. And this displacement graph shows the displacement of a single spot on the string or medium over the whole time, right? So we just pick a spot. And in our case, we're looking at, for the particle located at x equals 0. So if we look back over here, the particle located at x equals 0, what does it look like? What does the displacement look like at x equals 0 for a certain amount of time? And so we could imagine this shape passing by x equals 0. And then what does that look like? And so if we think about it, if this shape started out further back, so I guess, let's see, this is x equals 0. So let's say it started further back. As it's heading towards 0, this part of the wave is going to hit here first, and this part's going to hit here later. And so we can see that we have the shape is reversed, right? Because this part hits 0 first. So it hit 0, and then we go up here, and then this backside happens later in time. And so when you look at the two graphs, they look flipped, but it makes sense because this is hitting 0 first, right? So we see that the less steep part hits first, and then at a later time, the steeper part happens. So what about if we wanted to look at like x equals 1? So back over here at x equals 1, right, if it started back here, we'd get the same shape. So this part is going to hit 1 first, right? So it started back here at time t equals 0. And so it's moving, I don't know if it tells us how fast it's moving in this example, but it's moving to the right. And at time t equals 0, it hasn't hit 1 yet. It hasn't hit this spot yet because it's still back over here. So we have 0, and we have 0, and we have 0, and it just starts to hit at time equals 0.5 seconds. And we see again that this leading edge, right, hits this point at 1 before the backside does. So we should have this shape first, and then the more steep side coming after. So at a later time. So notice here, these are later times and these are earlier times. So let's look at an example. So here's a video that I thought was really interesting about history and snapshot graphs.
Comes up in waves, and so it's snapshot and history graphs, and I just want to try to explain the difference between them using this this little graphic here. So what we have is a wave traveling sideways, and we have this little red dot. The first kind of graph that we want to talk about is called a snapshot graph. So it's a snapshot graph is literally a picture of this graph at a single moment in time. And so as it's moving to the side, you just go click and take a picture, and what it looks like is the graph. So let's see what that looks like. So the wave moves to the side, and at t equals 27 seconds in this simulation, a picture of that graph is taken, and it's just exactly what it looks like with its position and everything at that time. The history graph is a little more confusing. So the history graph is what is happening at a single point over time. So the single point we're going to be considering is this red dot. And we're going to look at what happens to this red dot as the wave moves through the medium. So say this is just a red dot on a string, or it's a duck in an ocean or something like that on the water. So when the wave comes through, the dot first goes up and then down, up, down, up, down, up, down, up. And that's what gets plotted, right? The behavior of the dot moving up and down versus what the wave looks like at some instant in time. So here's both of them together. So as the wave moves to the side, the history graph tracks what's happening with that red dot going up and down. And then at one of those instances time, t equals 24 seconds, or 27 seconds, it gets a picture taken of it, right? And you see the graphs are actually the opposite of each other, and they have different axes. One is position, one is time. So this is the real difference between snapshot and history graphs.
Okay, so I wanted to show you an example of another example of snapshot and history graphs. So I'm going to show this. Okay, so I'm going to play this again. So notice we have our snapshot graph is at the top, and so notice that the axes are the same. So I have the y-axes are the same. So my y-axis is just the distance away from the origin, right, in both cases. And then the x-axis here is displacement. So this is a snapshot in time at t equals 10 seconds. This is what the wave looks like. And so what we're doing is we're looking to see for the history graph what happens at time at location t equals 10, at that location, at that dot location, what's happening? And that's going to be shown down here. So let's just play that again. All right, we'll play it one more time. And so just notice right here that right at t equals 10 seconds, right, we came right down this side. We went from 9 seconds here to 10 seconds here. And so we were at 9 seconds here and then 10 seconds here. And so notice the shape, right, is backwards. It's reversed. So when this wave headed towards 10, right, it was here at 0 and at 0, and then it started going up from here because this hit first, right? This hit first, this hit, right? So this is passing by this location where the red dot is, and then it falls off right here on the back. And so at a later time, the position at 10 meters saw the back of this graph. So that's why it's reversed. And so let's just look at this step by step. we can play this one, and we'll see. Let's just back up just a minute. And so at t equals 0, we can see right here that the dot at 10 meters is 0. And so that we should expect to see 0 on our history graph right down here, and we do. And so now it's just about to head up the side, and we see right here it goes from, up, my y value changes, and we can see that corresponding down here in my history graph. And as we advance, right, we can see it's climbing, right? And so we see that that's where the reversal happens. And now right now we'll be able to see it drop right down to 0 again. And then it's gone by, so it's not the wave has passed, or that shape has passed, and we would expect it to be 0. Let's talk about wave functions represent the shape of the wave as a function of position and time. So far we've talked about waves conceptually, but now we want to see how do we represent them mathematically. And so we can see here in our graph, we have something that looks like a spatial 2D area graph. But if you look at the axes, right, you'll see here we have, let's see if I can get my pointer out. That's the wrong one. I wanted this pointer. So we can see here we have the x-axis. So that's in space, right? What is my y value here as a function of position in the x direction. But then over here we have what is my y value in terms of the time, right? So we're representing time and the x as the variables, right, in this plane. And then the y value is represented as a disturbance, right? And so how do we represent that mathematically? Well, our y is a function of x and t, right? And so we're going to say, well, we're going to represent that by a sine wave where a is my amplitude, capital A is my amplitude. And then I need an argument that depends on x. So that's where my kx comes from, and omega t. That gives me the time varying piece. And then I have this constant out here that allows for me to pick my time t equals 0 or my x equals 0 value. And this kind of corrects for where the wave is. And k, we haven't talked about k yet. So far we have omega as our angular frequency, right? It's 2 pi times frequency, or 2 pi over the period. And so k is our wave number. That's what it's called. And that's given by 2 pi over lambda. So think about it as 2 pi, right, is one wavelength. And then we have 2 pi over lambda, right? So times x. So it's like, how many lambdas are we having? How many multiples of lambda? That's kind of what the wave number is telling us about. In this example, we have a figure of a snapshot graph at t equals 0 seconds of a wave moving to the right at a speed of 2 meters per second. And we need to draw a displacement graph for the position x equals 8 meters. So the first thing I'm going to do is I'm going to draw a dot on 8. Right here. So this is where we want to know. We want to know this snapshot graph shows us at time t equals 0 the wave at that time, where it is, right, and what the values are for the displacement at each value of x. And so what we want to do is we now want to have a displacement graph just for position 8. So a displacement graph means that we want to have a history graph. So we want to know what's going on at 8 meters over time. So the first thing I'm going to do is just continue to draw snapshot graphs for every 2 seconds. And the reason every 2 seconds is because the wave is moving to the right at 2 meters per second. So that means, I'm going to look at every second, and that way I know every second my graph is going to move to the right by 2 meters. So let's first, let me paste in here a couple of graphs so that let me just line these up. All right, so I just drew a couple of graphs here. And what I'm going to do is I'm going to draw the wave in 1 second. So at 1 second, at 0.8, in 1 second, I want to draw what's going to happen in 1 second to this wave. So I know in 1 second it's going to move by 2. So I know this position here at 0 is going to move over to 2, and this position 2 is going to move over to 4, and the position at 4 is going to move over to 6. So that just means that if we write 2, 4, 6, 8, 10, that means I'm going to have the same shape, right, as I did over here, just moved over by 2. And so this is t equals 1 second. Okay, and now what happened? And so notice what's happening at 8, right? At 8, right here, so let's put at like an X. Let's make this red again. So we're caring about 8 right here. This is 8 right here. All right, we're going to go back to blue. All right, and so what happens at t equals 2 seconds? So this is going to be t equals 2. Okay, so we know that in 1 second, so this is 1 more second, the wave at 2 is going to move to 4, the wave at 4 is going to move to 6, the wave at 6 is going to move to 8. So this is 2, 4, 6, 8. Okay, so we're going to go 2 to 4, so we're going to do this. Okay, so now notice at 8, right, it's still at 0. So far I've had at t equals 0, the displacement at 8 is 0. At t equals 1, the displacement at 8 is 0. At t equals 2, the displacement at 8 is 0. So what's going to happen next? Well, let's paste in some more graphs. Oops. Paste. Okay, let's line them up. Looks about right. I can go back to my drawing. Oh, I want to go down just a little bit. Here we go. Okay, so again, this is 2, 4, 6, 8, 10. All right, I'm going to mark my point at 8 is here. And this is 8 also. Go back to blue. Okay, so we've moved over again now. Now we've got 4 goes to 6, so that means we've got this. Right, so that's what it looks like. So between t equals 2 seconds and t equals 3 seconds, 8, the position at 8 has gone through this piece right here. See, this, oops, right here, that bottom of the wave, right, has gone through 8. And so we'll see what that looks like in just a minute. We're going to do one more graph. And we're going to say that we know that this is 8, this is 10, this is 6. Okay, so now 6 has gone to 8, so we know we've got this. All right, this is now 12. Now that's like that. Okay, so so this is t equals 4 seconds. Right, and now we know that in that between 3 and 4 seconds, this has gone through 8. Okay, so if we want to now draw a graph of, let's see, I've put in some more graphs here. And we'll line them up a little bit. It won't really matter. Okay, so now we're going to change this around a little bit. So I'm going to erase this because now we want time, not position. But our delta y stays the same. And so if we think about what's happening, we need to take the value at 8, right, of the wave as it's coming through. So we've got 0 for 1 second, 0 for 2 seconds here. And then between 2 and 3 seconds, it goes through the bottom of the wave. So let's see how we're going to draw that. So this is going to be time in seconds. So we said that at 0, the displacement 0, and at 1, the displacement 0. So this is 1 second. At 2 seconds, it's also 0. At 3 seconds, the bottom of the wave between 2 and 3 seconds went through. So I'm going to have this. All right, so basically so far we've got this. Now between 3 seconds and 4 seconds, the top of the wave went through. That's 4 seconds, and this is 5 seconds. And now after 4 seconds, we know that after 4 seconds, so in this example right here, this is 4 seconds, right? Then we know that right here 0 is going through, so the wave has already passed. So anything after 4 seconds, we're back to 0. So we're going to do this. Right, so this is our history graph, or our displacement graph, at x equals 8 meters. Right, so this is the whole time while the wave is going through, we're looking at position 8 meters, and we're looking at what happens at 8 meters, and this is what we see. And so we can notice that the shape is inverted, and that's because the leading edge, if I go back and look at my snapshot graph right here, this is my leading edge right here, and so this has got to go through 8 first before the back end does. And so since this goes through first, the bottom goes first, that's earlier in time, and so that's why we see that the graph is flipped for my last graph here for the displacement or history graph. In this example, we have a figure of a snapshot graph at t equals 0 seconds of a wave moving to the right at a speed of 2 meters per second. And we need to draw a displacement graph for the position x equals 8 meters. So the first thing I'm going to do is I'm going to draw a dot on 8. Right here. So this is where we want to know. We want to know, this snapshot graph shows us at time t equals 0, the wave at that time, where it is, right, and what the values are for the displacement at each value of x. And so what we want to do is we now want to have a displacement graph just for position 8. So a displacement graph means that we want to have a history graph. So we want to know what's going on at 8 meters over time. So the first thing I'm going to do is just continue to draw snapshot graphs for every 2 seconds. And the reason every 2 seconds is because the wave is moving to the right at 2 meters per second. So that means, I'm going to look at every second, and that way I know every second my graph is going to move to the right by 2 meters. So let's first, let me paste in here a couple of graphs so that let me just line these up. All right, so I just drew a couple of graphs here, and what I'm going to do is I'm going to draw the wave in 1 second. So at 1 second, at 0.8, in 1 second, I want to draw what's going to happen in 1 second to this wave. So I know in 1 second it's going to move by 2. So I know this position here at 0 is going to move over to 2, and this position 2 is going to move over to 4, and the position at 4 is going to move over to 6. So that just means that if we write 2, 4, 6, 8, 10, that means I'm going to have the same shape, right, as I did over here. It just moved over by 2, and so this is t equals 1 second. Okay, and now what happened? And so notice what's happening at 8, right? At 8, right here, so let's put it like an X. Let's make this red again. So we're caring about 8 right here. This is 8 right here. All right, we're going to go back to blue. All right, and so what happens at t equals 2 seconds? So this is going to be t equals 2. Okay, so we know that in 1 second, so this is 1 more second, the wave at 2 is going to move to 4, the wave at 4 is going to move to 6, the wave at 6 is going to move to 8. So this is 2, 4, 6, 8. Okay, so we're going to go 2 to 4, so we're going to do this. Okay, so now notice at 8, right, it's still at 0. So far I've had at t equals 0, the displacement at 8 is 0. At t equals 1, the displacement at 8 is 0. At t equals 2, the displacement at 8 is 0. So what's going to happen next? Well, let's paste in some more graphs. Oops. Paste. Okay, let's line them up. Looks about right. I can go back to my drawing. Oh, I want to go down just a little bit. Here we go. Okay, so again, this is 2, 4, 6, 8, 10. All right, I'm going to mark my point at 8 is here. And this is 8 also. Go back to blue. Okay, so we've moved over again now. Now we've got 4 goes to 6, so that means we've got this. All right, so that's what it looks like. So between t equals 2 seconds and t equals 3 seconds, 8, the position at 8 has gone through this piece right here. See, this, oops, right here, that bottom of the wave, right, has gone through 8. And so we'll see what that looks like in just a minute. We're going to do one more graph. And we're going to say that we know that this is 8, this is 10, this is 6. Okay, so now 6 has gone to 8, so we know we've got this. All right, this is now 12. That's like that. Okay, so this is t equals 4 seconds. Right, and now we know that in that between 3 and 4 seconds, this has gone through 8. Okay, so if we want to now draw a graph of, let's see, I've put in some more graphs here. And we'll line them up a little bit. It won't really matter. Okay, so now we're going to change this around a little bit. So I'm going to erase this because now we want time, not position. But our delta y stays the same. And so if we think about what's happening, we need to take the value at 8, right, of the wave as it's coming through. So we've got 0 for 1 second, 0 for 2 seconds here. And then between 2 and 3 seconds, it goes through the bottom of the wave. So let's see how we're going to draw that. So this is going to be time in seconds. So we said that at 0, the displacement 0, and at 1, the displacement 0. So this is 1 second. At 2 seconds, it's also 0. At 3 seconds, the bottom of the wave between 2 and 3 seconds went through. So I'm going to have this. All right, so basically so far we've got this. Now between 3 seconds and 4 seconds, the top of the wave went through. That's 4 seconds, and this is 5 seconds. And now after 4 seconds, we know that after 4 seconds, so in this example right here, this is 4 seconds, right? Then we know that right here 0 is going through, so the wave has already passed. So anything after 4 seconds, we're back to 0. So we're going to do this. Right, so this is our history graph, or our displacement graph, at x equals 8 meters. Right, so this is the whole time while the wave is going through, we're looking at position 8 meters, and we're looking at what happens at 8 meters, and this is what we see. And so we can notice that the shape is inverted, and that's because the leading edge, if I go back and look at my snapshot graph right here, this is my leading edge right here. And so this has got to go through 8 first before the back end does. And so since this goes through first, the bottom goes first, that's earlier in time. And so that's why we see that the graph is flipped for my last graph here for the displacement or history graph. Okay, so let's talk about sound. So sound is a longitudinal wave, right? So that, remember, that means that the medium, it's like the particles in the air are moving because the speaker has a membrane and it's pushing those molecules. So the wave is moving to the right, and we see a compression of those particles, and then place where there aren't any. And so that represents a wave. And you can look back in the video to the beginning to see an example of that, either with air, right, for a loudspeaker, or we talked about a spring or a slinky and how the coils come together and they spread apart, and that represents a wave as well. The speed of sound is different in different materials. So in air, the speed of sound is 343 meters per second. We can have the speed change with temperature. So the speed of sound depends on temperature. So if we have a typical day, our speed is going to be 343. So let's say that's, I don't know, 60 to 70 degrees. It'll be about 343 degrees. But if it's 0 degrees outside, our speed drops to 331. Our speed is different in different kinds of gases. So in helium or hydrogen, it changes. In water, the speed of sound is higher. If you think about a train, if you were to put your ear next to railroad tracks, you hear the train coming a lot faster, a lot sooner than you see it. And not that the light rays aren't getting there, it's just that it can be far away and behind mountains and things like that, and you can hear it coming. And so say you get off the railroad tracks, if you remember some of the old movies. But iron and steel, the speed of sound is about 5,000. In concrete, it's 3,000. So in glass, it's 4,500. So if you're listening for something, right, you'll hear it sooner in a metal than you will in air. And we can see that our temperature dependence for speed, actually, you can use an equation to calculate it. So V is equal to 331 plus 0.6 times the temperature meters per second. So we can actually calculate this 331 by looking at here, right? If our temperature is 0 when we plug in 0, then our speed is just 331. Some characteristics of sound that we need to know. One is loudness. So when we talk about loudness, we're talking about intensity or energy per area per time. If we're talking about pitch and how it sounds, we think about like high pitch and low pitch, and that has to do with frequency. And again, just to remind you, the audible range for human hearing is 20 hertz to 20,000 hertz, and you're going to be doing an experiment about that. We use a scale called decibels to measure sound intensity. And that's because we have a huge range for the sounds that we can hear for the human ear. And so the range is 10 to the 12 in intensity between the quietest and loudest sounds we can hear. And so we really hear on a logarithmic scale. And we don't typically like to talk about sound in terms of intensity or watts per meter squared, but you can see here the threshold of hearing is 1 times 10 to the negative 12. And the threshold of pain is 1 watt per meter squared. And so it's kind of hard to represent hearing with this kind of a scale where we're talking about something so small up to 1. And so we've just changed to a different kind of representation, right? A different scale that's called bells, or in our case, decibels. And so you can see here the threshold of hearing was set to 0, right? And the threshold of pain is about 120. So that scale is a little bit easier to use to talk about. But we can see here the equation that we use is beta. This is in decibels. So if we wanted to know a loudness in decibels, we could say it's beta. And it's equal to 10 times log of I, the intensity, right? And that would be a number in watts per meter squared, over this threshold, right? And our threshold is this value right here, 1 times 10 to the minus 12. And so if we use this equation a few times, we can either determine if we're given the intensity here, we can plug in what our intensity is in watts per meter squared, divide by this threshold value, take the log of it, multiply it by 10, and we'll get our loudness in decibels. If we want to figure out what our intensity is, we can go backwards and we can take log to the 10th power and we'll just get I over I naught. We can take beta over 10 and then that'll help us find our I, our intensity value. So just understanding how to take the inverse of log, right, is just take 10, take this value and raise it. So 10 to the power of log I over I0 just gives me I over I0. Energy is transported in waves. And so remember, if we think about a spring, right, energy is proportional to the amplitude squared, right? So we had energy is equal to 1/2 a squared when we were talking about springs. And so so we're saying energy is proportional to a squared, great. And intensity is just power over power over area. And so think about power. Power is proportional to energy, right? And so if energy is dependent on our amplitude, then intensity is proportional to amplitude. So intensity, remember, is power over area, and so we have power over 4 pi r squared. And so just remember that when we're talking about area here, the capital A represents amplitude of our wave, right? And a lot of times we represent area with a capital A, but in this case we're not. We're just saying amplitude of the wave is capital A. So on the numerator here, power, right? So power is proportional to A squared over 4 pi r squared. And so we can see that our intensity drops as the radius of the distance from the source. So our power or our intensity drops as we get further and further away or have a bigger circle that's representing our wave. This is the human ear, and so we're gonna watch a little video about that. But you can just see the interesting part. The sound comes in through here, right? It interacts with this membrane. The membrane moves. This is like a little piston that moves back and forth on the cochlea here, and the cochlea is being processed down here, and this goes into our brain. We can watch these two videos.
Many of us take for granted a very extraordinary organ, our ears. To understand the ear, we need to understand what sound is. The speakers you are listening to right now are vibrating, flexing in and out, causing a wave of pressure through the air. The frequency of these waves, or the speed at which the sound creating surface moves back and forth, affects the pitch of the sound. The level of air pressure in each wave is directly related to how loud the sound is. The outer part of our ear catches these waves. It faces forward and has a specially designed structure of curves, helping us to determine the direction of the sound and also emphasize the frequencies used in human speech. Now that the sound waves are caught, they travel through the ear canal and strike against our eardrum, a thin membrane about 10 millimeters wide. Now that we receive the sound, the middle ear transfers this energy. The smallest bones in your body, the malleus, incus, and stapes, start in motion. The malleus is attached to the eardrum, and as the sound travels along, the force is amplified by leverage until it arrives at the stapes, which acts like a reversed piston, creating waves in the fluid of the inner ear. The most significant increase in pressure is caused by pneumatic amplification. The face of the stapes has a surface area of about 3.2 square millimeters, while the eardrum has a surface area of 55 square millimeters. Using this, along with leverage to the malleus and incus, the final pressure is 22 times greater than when the sound first arrived. Now we come to the most complicated part of the hearing, the cochlea. In reality, it is coiled up, but it is easier to understand straightened out. There are actually 3 chambers inside, but let's take a look at the central part. The stapes is causing pressure waves to travel through the structure. Along the inside wall is about 20 to 30,000 reed-like fibers. As the waves move along, they encounter fibers with the correct resonant frequency and energy is released. These fibers aren't actually what give us the signal that we heard something. There is a special structure next to these fibers containing hair cells. When the fibers resonate, they cause the hair cells to move, which then sends an electrical impulse to the cochlear nerve and onto the brain. Certain pitches of sound will resonate in specific locations, and louder sounds will cause more hair cells to move. Our brain interprets all this raw data, making it possible to enjoy things like music or an engaging conversation. Just to think that all of this is happening in your head right now at full speed. This is just one of the amazing systems found in the human body that go far beyond our humble human understanding.
Okay, so this is the frequency response of the ear. And by the way, on this last slide, there were 2 videos, and we'll provide both of those to you in the resources in Canvas. So we're just going to talk about, again, the frequency response of the ear. You can see here that there's, on the left, we see the sound level in decibels, right, from 0 to about 120, right? From 0 is about the threshold of hearing, and 120 is the threshold of pain. And we can see the scale here, the intensity scale, watts per meter squared, goes from 1 times 10 to the minus 12 to about 1. Right, we can see the frequency change here. And so we can see that our hearing definitely depends on frequency. And so if we think about 20, this is 20 to about 20,000, represents our range of hearing. We can talk about wavefronts. So we've got 2 examples of wavefronts here. This one in the middle is a spherical wavefront, and the one on the right is a planar wavefront. And so the wavefronts are given by the peaks. So you line up and draw a line through all of the peaks, right? And that represents a wavefront. And so as it moves away, right, the wavefronts, you'll see, like, imagine dropping a pebble in a lake, right? These represent where the peaks are. And then we can talk about arrays. So array points from the source, right, and is perpendicular to the wavefront. And so that's showing the direction of motion of the wave. Here, right, my ray is perpendicular to the wavefront, and it's showing that it's moving to the right. And we'll be using rays a lot when we talk about optics, but rays represent the direction of motion of the wave, and the wavefronts connect the peaks. This is a great little video about the Doppler effect.
Good morning. The Doppler effect is named after Christian Doppler, a 19th century mathematician and physicist who was able to mathematically describe what is now called the Doppler effect. And it sounds like this. Perhaps you are already familiar with how the Doppler effect sounds. However, I'm here to make sure you understand why it sounds this way.
Oh, great. I always want to know why.
Me too. Actually, you know what? I do too.
All right. So it starts by recalling what this animation of a stationary sound source actually represents. So, Bobby, remind me, please.
Well,
Actually, rather than using the car horn, let's switch to a constant 440 hertz frequency being played on the speakers of the car stereo. That is the 440 hertz concert pitch, which we used last time.
it's harder to hear the Doppler effect at 440 hertz rather than the car horn. Can we just stick with the car horn?
Okay, we can go back to the car horn. However, the Doppler effect is easier to understand if we refer to a single frequency. So let's keep referring to the demonstration as a single frequency, but use the car horn demonstration. Sorry, Bobby. We're back to you. You are telling us what this animation of a stationary sound source actually represents.
Right. Remember, sound is a longitudinal pressure wave.
And those lines are crests.
Which are also called wave fronts.
Yeah, thanks. So sound is periodic changes in pressure in the medium, which in this case is air,
Each of those lines represents a crest in the longitudinal pressure wave. That means each crest or wavefront is a location of high pressure. That periodic pressure wave transfers sound energy through the air. And the reason all those circles are the same distance from one another is because the sound source is oscillating in simple harmonic motion at a constant frequency.
And do not forget that each circle actually represents a spherical pressure wave or wavefront going out in all directions from the sound source. It is a circle instead of a sphere here because this is a two-dimensional space.
Very nice, everybody. Now remember, this animation is for a stationary sound source. Look at how the animation changes when the source of the sound is moving.
I like that.
Good, but I want to make sure that you are aware that each of those circles, which are actually spheres, represent the sound coming from where the sound source was when it emitted the sound. To make that clear, I have highlighted one of the wave crests so you can see that it is a sphere that is increasing in size, and the center of that sphere continues to be in the location where the car was when the sound was emitted by the speakers of the car. Sometimes that is a concept which gets lost in the overall understanding of this.
Thanks.
Got it.
Okay.
Now let's add a human to our animation. Notice the human, or the observer, is currently located such that the car, the source of the sound, is coming towards the observer. Bo, what do you notice about the distance between the spheres that are going towards the observer?
On the side of the car where the guy is, the circles are closer to one another.
And what does that mean?
Well, the circles represent crests in the wave, and the distance between two crests of a wave is the wavelength of the wave. I guess that means that the wavelength of the sound wave which the guy hears when the car is moving toward him is less than the wavelength of the original sound.
Correct, Bo. The wavelength of the sound heard by the observer when the sound source is moving toward them is smaller than the wavelength of the original sound. And Billy, what does that mean for the frequency of the sound heard by the observer in this example?
Okay, the observed wavelength is decreased, and you are asking how that affects the observed frequency. Well, we know the speed of a wave equals the frequency of a wave times its wavelength. That means the frequency and wavelength of a wave are inversely related. That means if the observed wavelength is decreased, the observed frequency must be increased. In other words, when a sound source is moving towards an observer, the sound heard by the observer has a smaller wavelength and larger frequency. A larger frequency sounds like a higher pitch to us, so the sound we hear when the car is coming towards us has a higher pitch.
Absolutely correct, Billy. Bobby, could you please talk about what happens when the car is moving away from the observer?
Okay, this should be the inverse of what we just talked about. Now the crests are farther away from one another, so the wavelength of the observed wave is larger. Wavelength and frequency are inversely related to one another, so because the observed wavelength is increased, the observed frequency is decreased. That is why the frequency and pitch of the observed sound are lower when the car is moving away from us.
Very nice, Bobby, but I want to specify that the frequency and wavelength of the sound source remain unchanged. To reiterate that point, please enjoy this split screen of two different viewpoints during the demonstration. On the left, you see me in the car, and on the right, you see the event from the perspective of the stationary observer. Before we heard what was happening from the perspective of the stationary observer. Now let's listen to what we hear from inside the car. The frequency and therefore the pitch you hear is constant.
Sure, the person who is in the car is not moving relative to the source of the sound, so the wavelength and frequency they observe are not affected by the motion of the car. Thanks.
But what if it's reversed and the car is stationary and the person is moving? Great question, Bobby. That actually causes the same Doppler effect. If the sound source is stationary and the observer is moving, as the observer moves toward the stationary sound source, the observed wavelength is still decreased, and therefore the observed frequency is still increased. And the reverse is true as the observer moves away from the stationary sound source.
Good morning. The Doppler effect.
Okay, so here's an example of the Doppler effect, right? We hear this a lot when we're outside and we hear a fire engine go by, that as it's coming towards us, right? It's at a higher frequency. We can see the wavelengths are shorter, so the distance between the peaks are smaller. And so we're going to hear a higher frequency, and as it goes by, so here it's coming towards us, our wavelength here, this distance between the peaks is smaller, so we're going to hear a higher frequency. After it passes us, we're this person here, and now the wavelength is bigger. So if the wavelength is bigger, then our frequency is smaller, and a smaller frequency sounds like a lower pitch. If we want to do the calculations, right, we can find the frequency of the observer from this equation. So this F sub EM is the emitted frequency, right? So the source frequency, the frequency where it's being emitted, where it's happening. So where you're holding onto the horn in the car. And then V is the speed of the wave. V sub 0 is the speed of the observer, and V sub S is the speed of the source. And so V, the frequency of the observer, is greater than the frequency of the emitted wave when the source and observer are approaching, right? So high pitch. And the observed frequency is less than the emitted frequency when the source and observer are receding. And if we want to just do a quick check here, right? If our observer is not moving and our source is not moving, so if V0 is equal to 0 and Vs is equal to 0, then we have V over V as 1, and then the two frequencies are equal. So just a quick check, does that make sense? A sonic boom is an example of an object that's moving, and that where the speed of the object is catching up to the speed of sound, and a shock wave happens when that the thing that's moving is moving at the same speed or faster than the speed of sound. That's where the sonic boom happens. And so you get this shock wave. I think this is our last slide, and this is about ultrasound imaging. So ultrasound imaging uses really high frequencies, so much higher than human hearing. And I think it's somewhere around 2 megahertz where they use ultrasound imaging. And so what they do is they create this sound wave here. So imagine this is the abdominal wall. The wave goes through the abdominal wall, and what they're detecting is reflections from the different tissues in your body. And so some of the wave that's sent into your body will be reflected from each of the surfaces. So you can see that's the arrow to the left. Some will go through, and there'll be another reflection here against this surface. These are just example of what might be in your stomach, or an example that they use for testing. And then we'll have something here, like a vertebrae is going to have a reflection. There's some absorption, so the wave can be decreased. The reflected wave can be decreased because some is absorbed. Sometimes there's scattering, where there might be some of the wave might come in and then be scattered off, and it's not detected by the transducer. But what happens is you get these signals, right, at different locations and at different times, and they're able to take that information and create an image. So you can see here, these are reflections. And the color reflects the strength of the echo. So you can see the strength of the echo is much higher for vertebrae than it is for, say, adipose tissue or different kinds of tissue in your body. So just an example of a real world example of how sound waves are used for medical imaging.